All right, so welcome back. All right, this is a recap of yesterday. So we are now focusing on this principle GST1, right, which is Ginsburg Sands theorem for T1 spaces. So things have gotten a little bit simpler in terms of at least the statement. So we're saying every infinite T1 CFC space has an infinite subspace that is discrete or has the cofinite topology. That's our interest. And then we saw, or at least we haven't seen yet the connection to, but we started discussing ways of trying to break up combinatorial principles, in particular Ramsey's theorem for pairs, into kind of simpler versions. So the two we considered last time were SRT22, right, which again is talking about every stable coloring having an infinite homogeneous set. Stable, again, remember, means that the color eventually stabilizes for every pair of for all sufficiently large second coordinate, the color is the same. And there was this version, which we'll talk more about today, called D22, excuse me, which same statement, but rather than asking for a homogeneous set, you just want this limit homogeneous set, right? So everything in that set has the same limit color, but not necessarily locally is it all monochromatic the same. The other principle that sort of went with these was co. So this said every sequence R of sets has an infinite R cohesive set. Again, so this is a set which is not split into two infinite sets by any one of these sets, right? If you intersect with the set and its complement, it's almost inside or almost entirely outside each one of the sets in the sequence. And then the reason kind of why we were interested in this is this great theorem by Cholak, Jakish, and Slayman that Ramsey's theorem for pairs can be decomposed into the conjunction of these two principles. Okay? All right, any questions on that from last time? Okay, so then let's pick up right there. The idea of these kind of stable and cohesive parts became a really kind of prominent tool, really pioneered, made by Hirschfeld and Shor in their big paper on combinatorial principles in reverse math, right? So they kind of said, well, this is very fruitful for studying Ramsey's theorem for pairs. Let's do it for other principles, and in particular, they did it for ADS and CAC. So this is more for just general interest, right? So what would it mean to say that a linear order is stable? Well, it's a linear order is stable if every element is either small, meaning that it's below almost everything, or large, meaning that it's above everything, above almost everything, right? Excuse me. And that's if you sort of think through what that means, right? That's saying that the order type of that linear order is omega plus omega star, right? It has that shape. Every element is in an omega part or an omega star part, right? Why is that a notion of stability? I mean, you could imagine other notions of stability, right? And that's fine. This is a nice notion of stability because if you look at, I mean, one way to think that this is a nice notion of stability is to say, what is it that we want from a linear order in when we apply ADS? Well, we want a thing that looks like that, or a thing that looks like that, right? We want an ascending sequence or a descending sequence. And so what we're saying with this notion of stability is that we're somehow pointwise looking like that kind of in the limit, right? That's the idea. I mean, so that's a heuristic you can use to sort of think, well, how do you design useful notions of stability? The other way to think about it is that, and this is how a lot of these kinds of principles, stability is cooked up, is that you usually have a principle which is weaker than Ramsey's theorem for pairs. You have a natural proof of Ramsey's theorem for pairs of that principle. What if you look at, what would have to be true about this problem P? What additional property would it have to have so that your proof from Ramsey's theorem for pairs actually works as a proof from the stable Ramsey's theorem for pairs? Right? And it turns out that if you take the proof, so I assigned it as an exercise, right? But if you take the natural proof that say RT22 implies ADS, and you, instead of saying, okay, so what do you have? You say, given a linear order, you cook up a coloring so that every homogeneous set over here gives you an ascending or descending sequence, right? So if you use a stable linear ordering instead, then you'll see that the coloring you get by that process is actually stable, right? So you have the stability kind of percolating up, right? And that's another nice kind of notion that you say maybe we're on to the right notion. Okay, so this is a useful notion of stability when studying ADS. for CAC, it's actually kind of interesting. So Hirschfeld and Shor define stability to be this, which is maybe not what you would expect. You would say that a partial order is stable if either every element is small or isolated, or every element is large or isolated. So stability can be in one of these two forms. And again, why they used that was because it made the proofs kind of natural, right? So you have a proof, RT22 implies CAC. If you use this notion of stability, then the coloring you use in that implication is a stable coloring. So it sort of works more nicely. But you might anticipate, if you kind of don't think about the proof, but rather about sort of what is it we're trying to build? We're after all trying to build a chain or an anti-chain with CAC. You might think, well, this is a more natural notion of stability, where you say that every element is small, large, or isolated. Isolated meaning incomparable with almost everything. You might think that's a better notion. And it turns out, right, in this paper, they showed Jacques, Kestermans, Lemp-Lerman, and Solomon showed that they're equivalent. They're equivalent over RC naught. So you can use either one. They are not equivalent in all respects. For example, they have different arithmetical bounds, and they do behave differently. But if all you care about is sort of their strength, they are. All right. So that's sort of just an example. What about cohesiveness, right? So the whole benefit of the Cholak-Jacques-Slayman decomposition was that we broke a principle up into a stable part and a kind of complementary part. So remember, this is SRT22. We can similarly form a stable form of ADS, where we're now saying instead of every linear order has an ascending, descending sequence, we say for every stable linear order, right? And similarly for SCAC. And now we'd like sort of the other half, right? We'd like sort of the other half, and you might say, well, what should that be? Co sort of worked out to be a useful principle, but it there wasn't necessarily anything about it that on its face made it seem that this would be the complement to SRT22, right? So it's possible just to kind of systematically come up with the complementary, the cohesive version, right? And that's, if you, instead of looking at co, we could look at this version, this principle CRT22, and it basically says what co does, right? If you remember the decomposition, what did we do? We had a coloring, an arbitrary coloring, which did not need to be stable. We defined a certain family of sets such that when we got a cohesive set for that, our coloring became stable on that. Okay, does that make sense? That's what co gave us, right? Well, let's just take a principle that just says that that's possible to do. We know it's possible to do with co. So we could just say CRT22 is the statement for every C, for every coloring, there's an infinite set X on which that coloring is stable, right? Okay, so that's sort of automatically gives you the complement to SRT22, right? It's clear that plus SRT22 is going to give you RT22. Yeah? And in fact, it turns out that co and CRT22 are equivalent, at least if you assume B sigma 2. And it's still actually open whether or not they're equivalent over I sigma 1. But at least if you believe in the integers and in induction, they are the same principle. Okay, so you can use either formulation if you prefer. But the benefit of CRT22 is that it immediately tells us how we should formulate the cohesive version for, say, ADS and CAC, right? We just say, CADS is saying for every linear order, there's an infinite set so that the linear order restricted to that infinite set is stable, right? And similarly for CAC. Okay, so that gives us some nice versions, and they are not the same as co. These principles are in general going to be different from co, and these stable cohesive decompositions have been done all over the place. Erdos-Moser for lots and lots. And in general, they are not, the cohesive problems are not co. They are something like this, and they have distinct strength. And it's interesting to note that, okay, so we have the decompositions, obviously. In fact, the cohesive version for CAC is just ADS. So that's a nice kind of thing that we don't actually even have a separate principle there. Remember, ADS implies co. We had a proof of that last time. And in fact, that's a strict implication. We didn't prove that. But in particular, means that the cohesive form of CAC is strictly stronger than co. Right? So it sort of makes sense. You have a principle which is weaker than Ramsey's theorem for pairs, like CAC. Right? And it has some correspondingly weaker form than SRT22 of its stable form. So somehow the cohesive part goes up in strength. The intuition. Okay. All right, so let's think now about GST1. That's the new principle that we're studying here. So maybe we'd like to do something similar. And so let's fix a CSC space. Now, this is not necessarily a CSC space with any properties, but what could we mean to say that such a space is stable? Again, stability should be thought of with respect to some principle. So with respect to GST1, right? What do we want in a GST1 solution? We want either a discrete subspace, so every point has a singleton neighborhood, or we want the subspace to be the cofinite topology, so every open set is cofinite. So you could choose this definition, right, which is to say that a CSC space is stable if every one of the basic open sets is either finite or cofinite, right? Or you could even, if you want, say singleton. If every singleton is in the blank. For a T1 space, those are equivalent, right? And that's maybe worth noting that, right? That if you have you can work it out, right? That in a T1 space, all the open sets being finite is the same as all the singletons being. All right, so that seems like a reasonable notion of stability given what we just said. And in fact, it's interesting to note that this one follows, we can get such a space from a given CSC space by applying co in much the same way that we could get a stable coloring from an arbitrary coloring, right? So we have our CSC space here, and we apply co to what family? We don't have to cook one up. We just apply it directly to the basis, to U. So we get now a cohesive set for this. So we have an infinite set X, which is almost contained in UN or almost contained in the complement. Yeah? It's an infinite set, right? So if it's an infinite set, and if that infinite set is almost contained in UN, then UN is infinite, right? And it's cofinite relative to that set itself. Right? So if I take this cohesive set X and view it as a subspace, I have exactly a stable CSC space in the sense of this definition under the subspace topology. Make sense? Okay. So things are lining up nicely, right? We have a notion of stability which seems to make sense for one of the two heuristic reasons that I gave, right? We don't have an implication of GST1 from RT22, so we can't rely on some kind of natural proof of RT22 to this principle and then see what properties do we need so that SRT22 implies that version with those properties. But we do know what we want the solution of GST1 to look like, and we have a property that locally looks like that. Right? That's exactly the notion of stability that we have. And it's working nicely in that we can apply co. So we could also formulate one of these C versions of GST1, right? Say there's an infinite set so that when you restrict the space to that as a subspace, you have a stable space. But we don't need it. We can just use co. Right? Co itself seems to work okay. All right, so here's our stable form. And this proof here shows us that we get at least one direction of the decomposition. Right? SGST1, stable GST1 plus co implies GST1. All right. So let's prove the converse. Right? All right. So what we want to show now is that GST1, Ginsburg Sands for T1 spaces, implies, okay, clearly implies SGST1. It's just a restriction, so we need to show that it implies co. And what we'll show is that, in fact, GST1 implies ADS. We already saw last time at the end of the last lecture that ADS implies co. Okay? All right, so how do we prove this? So let's fix a linear order L. We're arguing in RCA naught plus ADS. And let's define, as usual, some sub-basic open sets from which we'll generate a CSC space, right? We'll generate the basic open set. So here's what we'll do. For each x, we're going to have sort of a special neighborhood Vxx. And what that is, it's just the lower cone of x under the linear order. And then for distinct x and y, we'll also have a special neighborhood Vxy, which is Vxx without y. So this, when we take the CSC space generated by this is automatically a T1 space. Does that make sense, right? As witnessed by this, right? Vxy and Vyx are neighborhoods, one containing x but not y, and the other containing y but not x. So it's a T1 space. Okay, so that's great. So we can apply GST1 to it, and let's see what happens, right? So let's say we get an infinite subspace y, It's either discrete or has the cofinite topology. If it has the cofinite topology, then what do we know? We know that, in particular, this neighborhood here, right? Every open set in this, every non-trivial open set in the subspace topology is cofinite. So in particular, this guy here, Vxx intersect y, is almost all of y. That means almost everything in y is below x, so x is large inside y. That make sense? Okay, so that gives us a descending sequence. And in particular, right, I mean, that's what we want, right, for a solution to ADS. Right? Every element in y is large with respect to the restriction of the linear order. So, all right, and if it's discrete, if y is discrete, then what do we have? Then for every x, right, there is some open neighborhood u in the basic open set, which intersected is just a singleton x. Yeah? And, okay, now this u is what? This u is an intersection. You can think about that, but when we generate the basis from the subbasis open sets are intersections of these subbasic open sets, finite collections of subbasic open sets. Yeah? So x then is equal to y intersected with finitely many things of this form, vxy. Does that make sense? And so what can we conclude from this, right? The things that are less than x then have to be contained in this finite set F. You can think through that if you want, but it follows directly from the definition. Right? Okay, so in particular, the set of predecessors of y under the linear order is finite. Linear order, that means it's above almost everything. Okay, so it's, it's set of predecessors, so it's below almost everything, sorry. So it's small, right? So everything in y now is small, and so this is ascending, and so we have ADS. And that gives us the decomposition, right? So we have an exactly analogous decomposition to the Cholak-Jacques-Flayman theorem for RT22. We have such a decomposition now for GST1. All right. But which is nice, but, you know, and it's nice that the cohesive version is that's also nice, but we actually are going to get even luckier, right? Where it's going to be even more interesting than that somehow. So let's make a definition here. Let's remember this D22 principle, right? That said that there's a limit homogeneous. Every stable coloring has an infinite limit homogeneous set. Remember that one way to say that was to say that given a delta 2 definable coloring of singletons, there's an infinite homogeneous set for that. You remember that, right? The delta 2 definable coloring of singletons was, this is the limit color of this element. Right? Okay, or if you want, given a delta 2 definable just formula, right, you have an infinite subset of the formula or of the complement of the formula, if you like. So let's make that a more general definition. Let's let gamma be a class of formulas, sigma 2, pi 2, something like that. And gamma subset will be the axiom schema that for each formula phi and gamma says the following. There's an infinite y, which either phi holds of everything in y or phi holds of nothing in y. Right, so that's what I'm thinking of as y is a subset of the formula, or y is a subset of the set defined by the formula, or y is a subset of the complement of the set defined. And under this definition, right, then we can see that D22 really is just delta 2 subset. Right? That's, again, for syntactic reasons, it's not quite the same thing, but morally it's exactly the same thing. And in particular, right, sigma 2 subset, the proof of that formalizes very nicely. Sigma 2 subset implies D22. Yeah? Now, D22 was SRT22, the stable form of Ramsey's theorem, was equivalent to D22, was equivalent to delta 2 subset. And it turns out that the stable form of GST1 is equivalent to sigma 2 subset. So it's really just like SRT22, but one quantifier up. Right? That's sort of the surprising part of this. Let's prove this, right? Because the payoff of this is that we'll know where GST1 lives. All right, so let's go from this in this direction first, right to left. So let's suppose we have sigma 2 subset, and let's derive from it as GST1. So we're going to fix a stable T1 space. Well, this is a stable T1 space, so for every point, right, either the singleton containing that is a basic open set, or all the basic open sets containing X are cofinite. That's the only option, right? All right, so let's let phi of X be the set of all, phi of X hold if the singleton containing X is a basic open set. And that is a sigma 2 formula, if you think about that, right? Because you're saying there is a position in the sequence so that X is in UN, and for all Y different from X, Y is not in UN, right? So it's sigma 2. And by stability, the negation of this, right, is exactly to say that if X is in UN, one of these UNs, then UN is cofinite. Okay, so we have a sigma 2 formula defining having a finite neighborhood. Right? Okay, let's apply sigma 2 subset to that. What do we get? We get an infinite set, so that phi holds of everything in there, or phi holds of nothing in there. If phi holds of everything in there, then each one of the things in there has a neighborhood, which is a singleton. And therefore, this is a discrete subspace. Right? It's not even the subspace topology. It's just discrete with the, you don't have to intersect anything, right? Again, if phi holds of nothing in there, then every single neighborhood of every single point in Y is cofinite. So this has the cofinite topology. Again, you don't even have to intersect it with it. I guess you have to intersect it for it to be a subspace, but all the neighborhoods are actually cofinite. So we have SGST1, right? We have a discrete subspace or a cofinite subspace with the cofinite. All right, this is the converse then, right? So now we want to prove sigma 2 subset. Here's a sigma 2 formula, and let's write it like this, right? Phi of X is exists Y for all Z, theta X, Y, Z, and theta is just bounded quantifier. All right, we have only SGST1, so we have to build a topological space, right? So let's do it. So what we're going to do this time is we're going to build neighborhoods that have this shape. VXYS, what that's going to contain is X, and then it's going to contain all these W's which are bigger than X and S, so that there's some witness below this W. So it's the set of all sufficiently large things that bound a witness to the formula not holding with Y. So there is a Z less than or equal to W, not theta X, Y, Z. And if we sort of think through it a little bit, we'll notice the following, right? So for a fixed Y, if Y witnesses that phi X holds, so for all Z theta X, Y, Z holds, then we're never going to find a Z like this, right? So VXYS is then just going to be the singleton X for all S. Make sense? If not, right, if this doesn't hold, then there's a least Z such that this holds for Y. And by the way, this is a bounded quantifier formula, which is then by assumption true of some Z. And I sigma 1 can then give you the least Z, right? So this is important to keep track of these things. So I sigma 1 is used there. And what do we have? We have that VXYS is exactly the set containing X, and all the W's bigger than max X and S for W bigger than this Z, this least Z. Right, so I could have, I guess, written as W bigger than max X, Z, and Z, right? Sorry. More human way of writing that. Okay. Does that make sense? So in particular, so there's two things to notice, right? So if this formula holds, then all these neighborhoods containing X are a singleton. If it does not hold, then they are all cofinite, right? And moreover, it's not just that it's cofinite. We know where the co-infinity starts, right? It's one thing to say cofinite, which is to say you contain all numbers from some point. But where is that point, right? That's not a computable thing to figure out. I1 question to say you contain all numbers bigger than this. But here we do, right? It's bigger than, okay, bigger than this because everything in here has to be bigger than this. But then it's bigger than or equal to Z for Z being the least witness to the formula not holding. Yeah? And that's important. That's important for this proof, right? So these sets are not just cofinite, they're sort of uniformly cofinite. All right, so summarizing this, we have that phi of X holds if and only if this is a singleton for some Y. and some S or all S, the S doesn't matter. All right, so let's take the CSE space generated by these subbasic open sets. The stable T1 space. Why is it T1? Well, it's T1 because of, again, this, right? We leave big gaps. We can leave gaps that omit any other number that we want. And it's stable by this argument here. Okay. And we have that if phi of x holds, then the singleton is in, the singleton containing x is in U. And if not phi of x holds, then here we have to make a little argument, right? We have that each basic open set containing U containing X is cofinite, which seems fine because each element of this is an intersection of things of this form, right? And we already argued that if this is, if phi of X doesn't hold, then all the neighborhoods are cofinite. But an intersection, in general, again, right, for this reason that I mentioned, in general, RC cannot prove that a finite intersection of cofinite sets is cofinite. You need B pi 1 for that, B sigma 2. But here they're uniformly cofinite. We know the places where they're cofinite from. Okay, so this goes through an RC not. Okay, any questions on that? Yes, for CSE spaces in general, where did I have it? Every U is either finite or cofinite. And in T1 case, you can say singleton or cofinite. All right, so this is the picture, right? So now we have a little snapshot of the zoo. So here's AC naught, here's RC naught, and the picture's very nice, right? Because I drew it that way. You can always make it, right? So here's RT22, and RT22 is this sort of champion among the zoo principles, right? It implies basically everything. Except for WKL and things that are kind of WKL-ish, right? It doesn't behave too well nicely with that. But almost everything else, I mean, almost everything in the zoo, this is definitely true, virtually everything in the zoo is a consequence either of RT22 or of WKL, or maybe both, right? There are things that are consequences of both. RT22 has a very special position in that, right? But here we have GST1 above it, right? Which is kind of surprising. And moreover, right, it sort of is above it because of nice reasons, right? It's because GST1 admits a stable form, just like RT22 admits a stable form. And that stable form has this very nice syntactic classification, just like this stable form has this nice syntactic characterization, right? It says delta 2 subset. And this is exactly the same thing with just one quantifier up. And then both of them, right, with co are equivalent to those stable versions with co, and that's how we get the implication. So we have a topological principle, and then we have this famous combinatorial principle, and they are somehow very similar, right? And that's a nice, I think, use of reverse mathematics, right? That's sort of something reverse mathematics does that I think is there's a lot of things we do in reverse math that many people outside of reverse math are not interested in, let alone, outside of logic, definitely not interested in. But I think you could go to a combinatorialist and say something like this, right? And there are many examples. I'm not trying to say this is somehow very special among that. But I'm saying these kind of results, I think, are ones we can talk to other mathematicians with and even say, like, look, this is a real, right? Somehow saying that they are connected, right? In a certain sense. Richard Shore has great examples of that too. If you ever talk to him at some conference, he has plenty of great examples of real non-logicians asking him about real theorems, right? And saying, hey, can you show that this thing is really needed in this? And so he has wonderful stories about that I'm sure he'd be happy to tell you if you ask him. Okay, but this is another example like that, right? All right, so in the remainder of the talk today, then, I want to talk about this interval. And there's two intervals exposed by this work, right? There's this interval, and then there's this interval. So today I want to talk about this one. And I won't be able to say too much about that one. But, so how do we show that GST1 is not, it would all be somewhere of sad if GST1 was just equivalent to AC naught, right? Then, so it isn't, that's a spoiler. But how do we show that? So I'm going to try to prove this. And here I'll be talking about a lot of the things that Ludovic already said. But I'll be talking about them sort of differently outside of a framework. So if you're comfortable with these arguments, now you'll see it with the framework argument. Now you'll see it sort of in a particular application. Otherwise, this is, maybe it's a way of seeing all this stuff again, right? Seeing it one more time. Okay. So what we want is to talk about cone avoidance. And remember that cone avoidance is relevant in discussing implications to AC naught because, in particular, right, as we discussed, every omega model of AC naught contains zero jump. And so if we can avoid computing zero jump, right, then we'll be happy, right? Because then we can hopefully produce a model of a principle that doesn't contain zero jump and therefore is not a model of ACA naught. Okay? So this is, just like in Ludwig's talk, a problem P admits cone avoidance if for every non-computable set C and every set B that doesn't compute C, every P instance computable from that B has a solution Y so that B join Y also doesn't compute C. So if you do it in the unrelativized case, right, like maybe you say, for every non-computable set C and every computable instance X has a solution Y so that Y doesn't compute C, right? That's kind of the idea. That's if B is the empty set. Right? All right, and the result that we need is that co admits cone avoidance. And we'll see in a sec how we sort of get model out of that. But here's a sort of stronger version, which Ludovic mentioned also in his talk, but I kind of want to maybe highlight a little bit more because I'm not sure if, at least the first time I sort of thought about these things, it wasn't always clear to me what the difference is. Right? So you have cone avoidance here. Here's strong cone avoidance. Strong cone avoidance is the exact same thing, right? So you give me a non-computable set C, you give me some set B that doesn't compute C, and now you give me a P instance X which need not be computable from B. It need not be computable from anything. Right? It has arbitrary complexity. Then X has a solution Y so that again B join Y doesn't compute C. Right? So that's strong cone avoidance. And that's a much stronger property in general. And this result of mine with Carl Jakisch is that RT12 admits strong cone avoidance. Now, why do we kind of want strong cone avoidance for RT12, or why is that useful, right? Okay, so co admits cone avoidance, and we'll see how to put things together to get a model in a second. RT12 admits strong cone avoidance. RT12 is not SRT22, right? It's not D22, but it's a delta 2 version of, sorry, I should say D22 is a delta 2 version of RT12, right? So if we're sort of thinking like, hey, give me a computable instance of, say, D22, right? And I want to say that has cone avoidance, right? Or something like that to build a model. Well, if I just had that RT12 admits cone avoidance, it wouldn't be enough. Because I don't have a computable instance of RT12. I have a delta 2 instance of RT12, right? Delta 2 in the given instance of D22. So I need this ability to elevate the complexity of the instance and still maintain cone avoidance. And that's exactly what strong cone avoidance does. All right, so it's, point out that D22 and sigma 2 subset also admit strong cone avoidance, right? Because they are just non-effective versions of RT12. Both of them are RT12, right? This is sigma 2 RT12, this is delta 2 RT12. So they admit strong cone avoidance simply because RT12 does, right? Okay. All right, I guess I said this already. This is all right. Okay, good. So let's move on. Here's an interesting fact, right, that shows that these properties, at least of strong cone avoidance, don't necessarily behave as nicely as you might think. So D22 is equivalent to SRT22. D22 admits strong cone avoidance because if you give me a arbitrary complexity instance of D22, I can produce an arbitrary complexity instance of RT12 and apply strong cone avoidance to that, right? But SRT22 does not admit strong cone avoidance. SRT22 admits cone avoidance, but not strong cone avoidance. And here's the proof. So let's define an instance of SRT22, which is not going to be computable, by C of XS is 1 if the enumeration of 0 prime up to x by stage S is correct. So this is some fixed enumeration of 0. Okay, so this is a delta 2 instance of SRT22 in the sense that we have 2 parameters, right? And it's stable, right? Because for sufficiently large S, this will of course be 1. Right? If S is large enough, 0 prime is correct. The enumeration up to stage S is correct, right? Up to x. Okay, so in fact, it's a very nice instance of SRT22 in that everything has the same limit color, right? So as an instance of D22, it's completely trivial because omega is a limit homogeneous set, right? It's a solution to it. But SRT22, if you had an infinite homogeneous set now where you thinned it out so that the local color was already 1, then you could compute 0 prime from that. You do not admit even the cone above 0 prime, right, with SRT22. All right, but SRT22 does admit cone avoidance, not strong cone avoidance, but cone avoidance. So let's do that argument, right? Suppose you have a non-computable cone. You have some set B that doesn't compute C, and now we have a B computable stable coloring. It's a big difference, right? Because this coloring here was not computable in something that didn't compute 0 prime. It was in fact 0 prime equivalent. Now we can define this delta 2, this induced limit color, right, of singleton. So D assigns to a number its limit color under this coloring. So D is computable in B prime. It's not computable in B, but that's okay. We can apply strong cone avoidance to this as an instance of RT12 and get an infinite homogeneous set for it, right? Meaning B join L doesn't compute C. And using B join L, right, really using L and C, but C is computable in B, we can now thin. We can now thin it out to get a homogeneous set. That make sense? But for that argument to work, right, we needed C to be computable in B. Okay. All right. Okay, so here's the nice meta theorem that kind of justifies our interest in this. So suppose you have even, as many principles as you want. You don't need just one. P0 through Pk, suppose these are all principles that admit cone avoidance, right, in the definition that we've been talking about. Then there's an omega model of RCA naught plus all of these principles in which ACA naught fails. Right? And the method of constructing this model is what we call an iterating and dovetailing. Right? So this is a very common model construction technique. So what do? We start with the empty set, and then we're going to build a tower of sets, B0 computable in B1, computable in B2, and so on, and let our model, right, this is an omega model, so I'm just have to specify the second order part, the sets. Let our model be just all those sets computable from some of the BN, from any of the BNs. That's computable from that tower. Yeah? And if I ensure, so this is clearly a Turing ideal, by the way, right? Since this is closed under joins and closed downwards. And what we're going to ensure is that none of these BIs compute 0 prime, therefore 0 prime is not in the model. So automatically this model will fail to be a model of ACA naught. Okay? So all we have to worry about is satisfying the PIs, right? The B0 through Pk. All right, so what do? All right, so let's start with B0 as just the empty set for starters. Suppose now inductively that we've already defined Bn and doesn't compute 0 prime, so everything's looking good. And let's look at n and decompose it as a triple, and suppose that triple is EMJ. Okay, and so just by coding, we can assume m is less than n, right? That's how pairing functions work. All right, so when we look at this, first thing we might ask is j smaller than or equal to k, so that j refers to one of these indices? You can always assume that, I guess, depending on what kind of pairing you're doing or what. But doesn't hurt to ask it. And then the next question we ask, and we're not doing this effectively at all, right? This is just a model construction in the real world, right? So depending on the next question we can ask is phi sub e for this e and b sub m for this m. So b sub m is less than n, so it's already one of the sets we've defined. Is that a PJ instance? Right, that's the next question we ask. And maybe it is, maybe it isn't, right? If it's not, we just set bn plus 1 equal to bn. If either of these questions, if j is like much bigger than k or something like that, we don't have to do anything. But if it is, then we have a legitimate instance of one of these problems, and we need to add a solution to it in order for our model to be a model of that principle. Okay, so what do? Well, we have a BM computable instance of PJ. PJ admits cone avoidance. BM doesn't compute C, so there's a solution. Why? So that, in fact, y join b, so this is a bm computable instance, but I can think of it as a bn computable instance, and bn computes bm, right? I can think of it as a bn computable instance. So I can apply cone avoidance to get a solution y so that bn join y doesn't compute c, and I make this my next bn, right? This is bn plus 1. Bn plus 1 is bn join y. Yes, Andrea. C is 0 prime. Thanks, yeah, good, yeah. Gavin, you had it? Oh, okay, sorry, yeah. C is 0 prime, unless otherwise mentioned. I just like calling it different things. All right. Yeah, so everybody clear on how this goes? Yeah, okay, and that's it, right? That's the model. And now if you look at the model, right, if you can sort of say, well, is it really a model? Well, okay, so it's one of those arguments, right? If you have an instance in there, then it's computable from some Bn. That means at some stage you considered it and you added a solution at the next level. Is what we need. Okay. Good. All right. So all we need to do is prove cone avoidance for co and strong cone avoidance for RT12, right? And we get our model of, well, so strong cone avoidance implies cone avoidance, right? So we'll have a model of co plus, right? P0 will be co and P1 will be SRT22 or D22, whichever one you want. And that will therefore be a model of RT22, right? But again, we have strong cone avoidance for RT12. This one theorem that already we know also gives us sigma 2 subset, right? Because RT12 at the sigma 2 level is sigma 2 subset. Right? So by the same argument, right, we can also take here co and then sigma 2 subset. And again, most of those principles will have cone avoidance. And so we'll have a model of co plus sigma 2 subset, which doesn't contain 0 prime. That'll be a model of GST1, which is not a model of ACA naught. So the same classical proof that separates RT22 from ACA naught can actually be used to separate GST1 from ACA naught. All right. That's why I said this just now. Sorry. Right. So using this decomposition, we get non-implication, and using this decomposition, we get that non-implication. Right. So for our purposes, the interesting thing will be that we can add that arrow then, that non-arrow. All right. Okay. So how do we prove anything here? So we're going to use Mathias forcing. So I can go through this fast, I think, because Ludovic already did it. But I have a picture. All right. So what's a Mathias condition? It's a pair, di. D is a finite set. I is an infinite set. Everything in D is smaller than everything in I. That's a Mathias condition. Condition EJ extends DI if everything in D is in E, and anything that's in E that wasn't in D came from I. Right? So D is a subset of E is a subset of D union I, and then J is a subset of I. J we call the reservoir, right? It's the set of potential elements that we can add to our generic. That's the idea. And we'll also this is convenient to say that a set G satisfies this condition if D is a subset of G is a subset of D union I, right? So you can think this is what a Mathias condition looks like, and here's my cool animation, right? So you add elements, right, by stealing them from the reservoir, putting them here, and shrinking the reservoir. You don't have to put everything from the reservoir. You don't have to, you can put whatever you want, but you can only put things from the reservoir into the generic, right? There's another. And that's how we build this sequence here that gives us our generic object in the end. Okay. All right, so here we have just, the version of like the Rassio-Sikorsky lemma that generics exist, right? So if we have a collection Cn of dense sets of conditions, dense meaning every condition can be extended into this set, right? So C0, C1, C2, each one of them is a collection of conditions, and each one of those collections of conditions is dense. Then it's possible to find a sequence of conditions, right, where you meet each of the CNs somewhere along the way. Right? A beautiful, important theorem that's somehow like super trivial, but it's very important, right? It's like a theorem that's whose importance far outshines the complexity of its proof. Right? Without this forcing, wouldn't be possible. Right? So it's very important. Okay, so for every n, there's an m, so that this condition is in Cn. And we'll call this a generic sequence. You can use a filter if you want, but I like sequences more. This is a generic sequence, and the union of the sort of the finite parts, these DIs, that's what we'll call our generic object, generic set, whatever. Right? That's the thing we're building. All right. So what are some obvious things that are always dense? Well, for example, the set of conditions with number of elements in the finite piece being bigger than n is always dense, right? And so it's dense, right? The terminology we would use is to say it's dense to add more elements to the finite piece from the reservoir. Okay. What else? So this is something Ludovic mentioned here. Suppose we have a cohesive set, an instance of a sequence of sets. Excuse me. The collection of sets conditions di so that I is a subset of Rn or I is a subset of Rn bar, the complement, that's dense. Right? Because if you give me any condition di, either I intersect Rn or I intersect Rn bar is infinite. Right? And that's the only clause at this point that we've put on this forcing. Right? So what would a generic that meets this set for every n look like? It would be a cohesive set for this family. Does that make sense? Right? So there'd be some finite piece that may be the condition already established, but then we would pass to a condition whose reservoir is entirely contained in Rn or entirely contained in Rn bar. So any generic that begins with that finite piece would now entirely continue inside Rn or entirely continue in the complement of Rn. Does that make sense? It would be almost contained in one or the other, right? Yeah, so Matthias generics are always cohesive. Right? Okay, so that's the proof there. Okay, and we're going to use this kind of terminology of saying sufficiently generic. Just means meeting all the dense sets Cn that we care about, right? Whatever we need. All right, so let's do, I think maybe there's time in 10 minutes to do a little bit of this. So let's prove that Co admits cone avoidance. And what we're going to do is, okay, so we're going to fix C not computable in 0 prime. So think 0 prime if you want. C not computable in 0, right? Not computable C. Think 0 prime if you like. And some B that doesn't compute C, but for just simplicity, let's just take B to be the empty set, right? Don't worry about the relativization. So what do we want to do? We want to build here's an instance of Co that we fix, R, so we can think it's a computable instance. And what we want to do is build a generic that is cohesive, right, for this, but that also doesn't compute 0 prime. So we need to meet some requirements, so we need G to be infinite, so we're going to have requirements Qn for all n that say G is bigger than or equal to n. We're going to have requirements Rn that say it's cohesive, right, that it's almost contained in Rn or almost contained in Rn complement. And then we're going to have these big ones which say, this should be an E, sorry, say that phi e to the G is not C. Okay? And again, if we were using B, that requirement would look like that, right? And everything would be the same. No difference. So what we're going to do is we're going to restrict our forcing a little bit. We're going to say our conditions are Matthias conditions, but we want all our reservoirs to be computable sets. And you can sort of think through that a little bit, right? And notice that everything I said on the previous slide is still true. It's still dense to make generics infinite. It's still dense to be cohesive, provided the instance of Co that you're working with is also computable, right? Because remember that on this slide, right, I needed to intersect I with Rn. So if Rn is computable, then this is still computable, so it's all good. Right? But that's what we have here. Okay? So what we know, well, I guess we have we'll take a G to be sufficiently generic for this. This generic will then still be infinite, and it will still be cohesive. It will automatically sort of be cohesive for this family. So the real thing that we need to worry about is this. How do we, with this forcing, satisfy this requirement? Any questions at this point? All right, so how do we do that? So let's fix, this should be an E again, my apologies. So this is an index of some functional. Here's an arbitrary condition, and what we want to do, we're proving a density fact. We're proving every condition has an extension that satisfies SE, right? That requirement of not computing C via phi E. So here's how we do it, right? Here's our arbitrary condition. We're going to exhibit an extension of it. We're going to ask if there's an E-split, which, if you remember back to your computability day, proving things about minimal pairs and things like that, right? That's a term that shows up. So an E-split here, I'm going to say, are there finite sets F0, F1? Think of these as potential continuations of my finite set D. Are there finite sets F0, F1 in the reservoir? And is there some X so that both of these computations converge, but they're different? Right? So phi with F0 attached to D or F1 attached to D, both of them converge and are different. So that's an E-split over D, right? All right, so if there is, then that's great, right? Because at most one of them can be equal to C of X. Okay, so one of them, let's say this guy, phi E F0 of X, is different from C of X. And what we do is we take our extension then to be D union F0, and we're going to take I, and we're going to delete everything below the use of this computation, just so we preserve this computation, right? So the computation goes along and asks some questions about it needs some numbers to be in the oracle, some numbers not to be in the oracle. That might give you some huge use. Whatever that is, we're going to delete everything. And all the positive information is in here, and we're going to delete all the potential negative information from the computation. Everybody okay with that way of sort of thinking about functionals? Yeah. Okay, and that's now an extension, right, of this guy, because F0 came from I, and this is a subset of I. So we have an extension, and this extension forces that G satisfies SE. In fact, it forces it in this kind of strong way that Ludovic was talking about. Right? It's not actually even real forcing. It's true of all sets that satisfy whether they're that satisfy this condition, whether they're generic or not. Okay, so what about if not? Then you have the classic E-split argument, right? This is always the kind of backup argument you have when you don't have E-splits. You're going to claim that something is computable which should not be computable, right? Because all computations agree. Okay, so if not, then we're claiming that actually this is our extension that we can keep with, we can stay with, right? Because suppose you have any set S which satisfies DI. Satisfies, remember what that means, right? D is a subset of S, and S, anything outside of D in S is in I. Right? So D is sort of that path through in the picture, right, of the condition. Let's suppose this is total and equal to C. Okay? I claim that's not possible, but let's consider the case that it is. Well, then what can we do? Then, given this condition and given any X we want, right, we can search and find in a uniformly in X a finite subset of I so that this thing here converges. How do we know that we can find it? Because in particular S, phi e to the S of X converges, and S is D union something, right? And computations only use finite information, so some initial segment of S will certainly serve as F, right? So we will find it. We might not, of course, find an initial segment of S. That we don't know how to do because S may not be computable, but whatever we find has to agree with phi of S because there's no E-splits. Okay? So this gives us a uniform way, computably in I reservoir, to compute C of X. Oh, and then the last thing, sorry, that I didn't mention is that what we get in that way then is C of X by assumption, right? That phi of S is C, right? So this gives us a uniform way in I to compute C, and that's bad, right? Because I is computable and C is not. Okay? So if you think back to Ludovic's nice framework, right, for organizing a lot of these arguments, these are exactly the kind of case analysis that he had. The case 1, case 2, case 3, right? This is the degenerate case at the end, right, where you always argue that something's not possible. Okay? All right, so this gives us cone avoidance of Co. All right, let me say something real quick here just to set up things for next time because I don't think I'll have enough time to finish this. But let's start in the last sort of 5 minutes here talking about strong cone avoidance of RT12. So now we want to prove a stronger result, right? Now we want to prove, we want to fix an instance of RT12. The way we're going to think of that is, okay, so the setup is the same. We're going to take a non-computable set. We're going to take some set that doesn't compute it that we'll use as an ambient oracle, but we'll just take that to be the empty set for simplicity. And this instance now is arbitrary, so it's not necessarily computable, it's not necessarily anything. Let's think of this as a two-partition, right? Because that's what it is. So let's write A0 for the set of things that are colored 0 by it, and A1 for the set of things colored 1. So we have sort of a set, right? We have a set, and we want an infinite subset of one or the other. Either an infinite subset of A0 or an infinite subset of A1. And what we're going to do is we're going to assume that neither of these sets has an infinite subset G that doesn't compute C, the thing we want. Okay? So we're going to give a proof by contradiction, right? We're going to make that assumption. What we're going to do here is we're going to build two sets, G0 and G1. G0 is going to be, both of them are going to be infinite, so we want to satisfy this requirement for every n. And G0 is going to be a subset of A0, G1 is going to be a subset of A1, so we want to satisfy this global requirement here. And then we're going to have a disjunctive requirement, right? So sometimes this is called a Lacan disjunction. So for every pair E0, E1, we want to prove either that phi E0, G0 is not C, or phi E1, G1 is not C. Right, and this is this kind of nice thing that if we satisfy this for every E0, E1, then in fact, either phi G0 is not C for every E, or phi G1 is not equal to C for every E, right? And why is that, you know? If it was, right, if this equals C and this equals C, take the E0 and the E1, and now you fail this requirement. But it maybe seems like magic the first time you see it, right? That it somehow works. Okay, so we need to do this kind of disjunctive thing because, in fact, it is possible to build delta 2, let's just say, colorings of singletons so that every homogeneous set of, say, on the 0 side computes 0 prime. Right? So the fact that this always has an infinite subset, if you like, an infinite subset of A0 or A1 that doesn't compute 0 prime, that's true, we're going to prove it, but it isn't necessarily true that you can find an infinite subset of both A0 and A1. There could be very complicated subsets of A1. Just means the subsets in A0 are very, very easy. So the disjunctive nature of this is kind of is necessary. All right, I think that's a good place to stop. So we'll start off tomorrow by proving this, right? Actually developing the forcing and finishing this. All right, thanks. Thanks.